Checking. Is everything good? Okay, I will start my timer as well. So thank you, everybody. Thank you, everyone, for being here today, either physically or online. So I feel like it's really also pretty representative of this PhD in co-tutor by spending half of this program in France and in Australia. So I'm very grateful to be able to present with you my work entitled Reinforcement Learning and Sim Theory Transfer for Adaptive Control of AUV. And so before starting getting into details, I wanted to start with some underlying ideas that have bring me to do this research and that have pushed ourselves toward this research question. And the first idea is that autonomous vehicles are becoming increasingly prevalent in our day-to-day activities. So we've been able to see a lot of development in autonomous car, especially, but it's also true in other domains such as aerial drones, where this type of vehicle are being more and more used, for example, for delivery of medicine in very poor area. And the second idea is that with the recent breakthrough in deep learning, we are changing our way. So control designers are changing their way of methodology of how we design control system for such vehicles. And so with the recent breakthrough in deep learning, especially, we are starting to be able to consider more and more complex vehicle and more complex processes. And so given these two situation, the thing is that I've been able to see that there's still a contrast in the underwater domain, and so in maritime engineering in general. So we cannot see the benefits of this breakthrough in this domain. And so the big why of the starting point of this research was why and how could we leverage this change for underwater robotics. So in order to tackle
Thomas,
this challenge, yes.
hold on. It's not moving. Ring.
Okay. Sorry. All right, like that.
Yes. Yes. Okay.
So you can go back a little bit if you want. It's up to you.
Yes. I'll come back to this. Sorry for for this. Yes, thanks. Okay, so we'll just come back to this. So yes, the starting point really was how, why do we observe this kind of contrast in the evolution, in the dynamics of research and deployment of technology in the maritime domain? And essentially, we were interested on how we can contribute to the development of this type of new method using these new technologies. And so in order to do that, we tackled in this PhD thesis, we were focusing on the control of underwater robots, underwater vehicle in particular, named AUV, as the one you can see in the top right pictures. So this kind of torpedo-shaped vehicle. So we were interested on how we can design control system for this type of vehicle and also for cubic-shaped one. And so the control of these vehicles are very challenging because they are essentially associated to two main challenges. At least that's the two main challenge we were focusing in this thesis. The first one is unknown dynamics. So because of their small size, these vehicles have to compensate for the disturbing forces acting on their body, so, which come from wave, current, and also surface wind. And the problem here is that most of the time we are very limited on the sensors on board, which does not allow us to measure this type of disturbances. And on the other hand, furthermore, we are also limited on our ability to model this kind of chaotic disturbance. So it's very challenging to compensate for them, to compensate for disturbances that we cannot observe. And the second challenge is non-linearities, in the sense that usually this type of vehicle are used for applications such as inspection of offshore structure, or for defense applications such as underwater mine countermeasures. So we essentially send this vehicle where we don't want any human operator to be. And so it's very critical to not lose them. So we really caring about failures mode, and they also have to evolve in a very dynamic environment. So the controller response have to be pretty overly conservative in order to maintain the performance over a wide range of operating conditions. And so it was really the starting point that have been the main focus of these two challenging have been the main focus of this study. So here I've just drawn a kind of a map of the spectrum of all the research we've done over the past last 3 years, but we will essentially focus on what is highlighted in red in this presentation. So in order to solve this problem where we have a very dynamic environment, we have changing operating condition, historically was proposed in the late 1916 what is known as adaptive control theory. And this theory relies on the idea that we can adjust the controller response in order to adapt to the operating conditions. So it was initially proposed for the first hypersonic aircraft as the X-15 aircraft you can see on the picture. So this kind of vehicle have to operate also in a very changing environment, so at different altitude, at different speed. And so it was found at that time that linear, fixed, robust control were not enough in order to ensure required performances. And so it was developed at that time what is known today as gain scheduling method. And so this is known as what we call now model-based adaptive control, because we start from a model, from a mathematical representation of the physical law of the system. And so this was the first attempt at designing an adaptive controller. And so we found that this type of method cannot be used straightforward in our case. So for recall, we are in the case of very small size vehicle. We have limited sensors on board. We essentially only have an IMU on board, so we cannot measure the disturbance. So we are facing things that we do not know how to model. So these current disturbances, we don't have a perfect model of it, and we cannot measure it. So things that we cannot measure are the things that we are trying to compensate. And most of all, the gain scheduling method I just was just talking about usually require a lot of intensive simulation in order to be designed effectively, and which is very hard to do in the underwater domain, because water simulation is very expensive to run. So we really cannot rely on model-based adaptive model only to design such controller for our system. And so this is kind of the agenda for this presentation, really just to be briefly giving you an idea of what we're going to go through, but I won't be able to review every material from the manuscript, but we'll have plenty of time to do so during the question later on. So first, what we've been trying to do in our research methodology is to see in the literature what people have been doing. And what we found is that most recently in the underwater domain, people have been using what is known as learning-based adaptive control. And learning-based adaptive control is based on this idea that we can use some model-based structure control to control effectively in an optimal way the known part of the process. So everything that we know how to model with this model-based structure, and we can compensate for the unknown part with some model-free learning algorithm. So the idea of learning-based adaptive control is really to combine and get the best of the both worlds in one unique control system. And so among all the different model-free learning algorithms that exist, deep reinforcement learning is actually leading the field, and especially in the case of underwater robotics. So we'll see later why is it the case. But in our approach, we thought that was a good starting point to explore. And so deep reinforcement learning essentially are being used in order to adjust the controller parameters or the controller response to variation in operating condition. And the overall ambition is that since usually deep reinforcement learning are used in trained in simulator, the big question is how can we design a method that we sure that what we learn in a simulator will remain valid in the real world. So that was the overall ambition of this thesis. So how can we ensure that what is valid in one domain will remain still valid in another one? So in order to do that, to guide even more our research, we started with literature review. So here I've just listed some of the work that have been described in the thesis. But essentially what we've been able to observe is that people in AUV adaptive control, in learning-based adaptive control, what people have been doing mostly is to use deep reinforcement learning in order to tune a PID type control loop. So PID type are still consist mostly of most of the majority of controllers in the maritime domain are based on PID law. More than 90% in industry and in commercial uses are based on PID, whether they are in cascade or another variation. But most of the time we see PID controller. And so what we've been able to observe is that people have been using deep reinforcement learning to perform gain scheduling directly. And people have been also using mostly deterministic reinforcement learning algorithms such as DDPG, PPO, or TD3 most of the time. And so the idea now is that we've been able to observe some limitation where people would try to incorporate some stability component also in the control loop, either by adding some terms in the reward function directly, or either by constraining the output of the neural network directly. And so we wanted to develop a methodology would rather put constraint at the highest level, so as at the input, in order to ensure that whatever such learning-based algorithm would estimate will still hold some stability component. So following this first exercise, this first study, we, based on this work, we started to do some preliminary works where we try to design such a learning-based adaptive controller. So first, very simply, we compare a fixed PID controller, so an optimal PID controller whose parameters have been optimized using some model-based methods. So from the mathematical modelization of the vehicle, we can determine gains that are optimal for a given range of disturbances. And on the other hand, we just train a deep reinforcement learning algorithm in a sort of end-to-end fashion where we directly try to learn the control inputs, the power input to apply on the thruster. So this is not this is more like a purely model-free adaptive controllers. And so what we find is that even though both controller kind of succeed at completing a target rallying mission, the PID controller, even though it's not adaptive, were way more robust and were way more efficient at completing the task. So the trajectory performed by the PID control structure were way more satisfying than the one from the purely model-free deep reinforcement learning controller. And so this, from this study, we were really believing that there's something truly unique and truly significant from the PID control law that we want to keep in the loop. So in a second study, we started to we proposed the first design of a learning-based adaptive controller. This time, we try to keep the PID controller in the loop. And so we propose, again, the same purely model-free controller. And this time, we propose a learning-based adaptive controller where essentially the deep reinforcement learning algorithm is now adapting the pores of the gain, sorry, of the PID controller. So the idea is that now what happened when we keep the model-based structure in the loop combined to the model-free algorithm. And what we found was pretty interesting. On the left, this is the training curve. So on the left, we have the mean reward, and on the right, we have the success rate over training. And what we found is that thanks to the model-based structure, the learning-based adaptive controller is able to take way better action early in training compared to the model-free controller. And even though they kind of converge toward what seems to be very similar performances, in evaluation, the learning-based adaptive controller were the best controller out of the three. So the purely model-based fixed controller had a very a lot of struggle to complete the task. Meanwhile, the learning-based adaptive controller were able to complete the task even in mission where that was not observed at all during training. So that was already a good start supporting our first opinions. And finally, last preliminary work consists in assessing the stability of the controller. So just for disclaimer, in this study, we didn't build a learning base, a purely Lyapunov-based learning-based controller, in the sense that we didn't constrain the learning-based controller in the Lyapunov-based space, where we know the parameters of the PID are stable, but we just assess the difference between the stability of a purely Lyapunov-based controller and our learning-based controller. And what we found was really interesting is that on the left, we found that both controller display a same amount of stability in terms of state of the vehicle. So even though we don't take at all any stability component in the optimization in the learning process, we still match the purely Lyapunov-based stability. But on the other hand, we don't match at all the stability of the controller parameters. So that was also just a study to assess how stable we can, how much stability we can expect from a learning-based controller despite using neural networks. So following this preliminary study, we then tried to design our own. So we were able to identify the limits and where there were contribution to do. And so first of all, we started from the PID controller again. So as I said, we've been able to see that most people were using deep reinforcement learning to perform gains tuning essentially. And so the problem with that is we believe it's not very straightforward for a control designer to work in the gain domain. So we would rather like to design our control structure based on very high level physical insights. So from very desired control performance, for example, depending on the task, we want to have a very low overshoot, especially in the defense domain and so on. And so this is not very straightforward to do in the space of gains. And so we propose instead to work in the domain of poles, where it is way more easier to set our desired value based on this physical requirement, based on how much settling time we want, how much overshoot at maximum we want. And so because we are working on the PID control law, so the idea is that we wanted to propose a method that can be applied to any process where feedback control can be used. So essentially, whenever you can use a PID, that's where we want our method to be able to be used. And so because the PID control law have three gains, we propose a symmetric mapping in order to transform from the space of gains to the space of poles. And so this is why we essentially at the end can write each of the PID gains, so Ki, Kp, and Kd, in terms of this pole value, τ1, τ2, and τ3. And so what we arrive at the end is this type of cubic shape space of poles where we know each of these poles are of each of these poles for any value of the tau we take, the pole will be on the left half plane. So we know we have some convergence component holding in this design. And so now that we are working in the space of pole, it is way easier to define our bounds based on this desired performance. So it's really easy to define the minimum value and the maximum value of the poles based on how much effort the vehicle can produce, and based also on how much we would like ideally have of overshoot and desired settling time. So this is known as a adaptive pole placement strategy. So there's a lot of way to do adaptive pole placement. Now that we have this space of desired value, we know that for any value the neural networks will choose in this space, we will have some stability components on the control law. But now how can we choose which value is the best one? And so essentially, again, since we do not have access to any measurement of the disturbance, we propose to use deep reinforcement learning in order to explore this space and to estimate at each time step which pole's value is the best one for the current operating condition. And so if we would have a perfect knowledge of the process, we could use your favorite algorithms such as LQR optimization criteria. But in this case, we do not have access to that. So we propose to use a learning method to do so. So now that we have our model-based structure and our adjustment mechanism design, let's see how we can incorporate deep reinforcement learning into the loop. So again, as I was saying, most of people were using deterministic policies in learning-based adaptive control, and we make the choice to use instead the stochastic policy. And so in stochastic policy, essentially, we will represent each pole value by a Gaussian distribution. So this way we can take into account uncertainty on the disturbances and uncertainty on the process. So the output of the neural network will actually be the parameters of the Gaussian distribution, which represent the action distribution. So the mean and the variance of each Gaussian distribution are estimated by neural networks. So this is known as stochastic reinforcement learning. And so in order to build this stochastic mapping, we propose to use maximum entropy reinforcement learning, which is composed of first an actor-critic architecture, maximum entropy framework, and of an off policy formulation. So actor-critic is very classic architecture in reinforcement learning. It is composed of two elements, one actor, so the actor chooses which action to take, and a critic, which tells the actor how good this choice was. And essentially, this is an iterative learning process where each of these model will improve together until convergence to the optimal policy. And so here, essentially, this process can be framed as a Markov decision process. And essentially, using Bellman equation, we have a mathematical formalism where we can estimate, we can consider the Q value as the sum of discounted future reward, as you can see here. And the optimal policy now is just associated to the policy which at each action take the action that is associated to the maximum Q value. And so here again, the idea is that we want to build a policy which at each action estimate the best power value for each degrees of freedom in order to derive the Ph.D. Control law at the end of the day. So one big problem of reinforcement learning now is exploration. So because essentially reinforcement learning are really the policy at the beginning of training are essentially random. We can very often end up overfitting to suboptimal trajectories. And I try to illustrate this idea with this graph here. So let's consider we have our agent starting from this point here in green, and the goal is to reach the target, which is behind this ship. And so let's consider now the only way to reach the target is to go through the right path, the yellow one, and to contour the ship, and it is not reachable at all by the left. So essentially, if the policy is random at the beginning, we can expect the distribution to be equalized, to explore both paths in a normal, we will expect the agent to explore both paths quite equally. And so because, for instance, we can have a very classic reward function, we would be a function of the distance to the target, for example, a Euclidean distance, we can end up with a Q-value distribution like the one described by the orange curve on this graph. So essentially, the Q-value distribution will be higher on the left path compared to the right path, because the distance will be smaller when we go through the left, but the target will be only reachable if we go further right, even though if the distance increase. And so really what people in the community back then tried to formalize a mathematical framework in order to ensure that we pass through both paths equally. So one idea would be to have a positive transformation of the Q-value distribution. So instead of exploring proportionally to the Q value, the space, we would like to explore more fairly the space. And a very relevant candidate for that is the Q value, is the exponential, transformation. So the exponential transformation will, which is here just normalized by a function z, but it's just to represent the normalization. But the idea is that by exploring the space proportionally to the exponential of the Q value, we will more likely explore both paths more equally. So the negative value will be transformed into positive but small value. So we are sure by doing so that we will pass by the right path at some point. Because if we don't do, because in reinforcement learning, we essentially don't learn what a good action is, but we learn what which action is better than the others. So at the end, if the we use the traditional Q value exploration, the probability to go through the left path will keep increasing, while the probability to go through the right path will decrease until we will never explore it again. And so by considering the exponential of the Q value, we are sure that we will still explore both paths always until the true optimal trajectory is fine. And so it was found that it's very easy to build such policy. We can do so by minimizing the Kullback-Leibler divergence between the policy and the exponential of the Q value. And what we found is that if we write up the definition of Kullback-Leibler divergence, this optimization function is then equal to the max of the exponential of Q value and the negative log of the policy. And so for those who are very familiar with, for example, information theory, you might have recognized that the negative log of a distribution is essentially what is known as entropy. So entropy is information theory known how to describe how predictable a distribution is. And so this is very interesting because if we want to explore the space proportionally to the exponential of the Q value, this is essentially equal to maximizing the reward and the entropy of the policy. And this is very kind of counterintuitive because here we tell the agent, take the best action while being the more random as possible. And this is contrary to optimal control theory in general, where we are interested in taking the best action at each time step. But this is more a reference to what we call inference control, where we ask ourselves, given we are optimal now, which action were taken. And so by maximizing entropy, we ensure that the policy during training is forced to explore suboptimal trajectory, such a way that during evaluation, it will be able to solve a task even in a new domain because it has been forced to solve a task in a very great variety of ways. So maximum entropy essentially improve exploration during training and robustness during evaluation, which is why we chose this algorithm, because we have a lot of uncertainty against unobservable disturbances. And the first point, the last point, is the off-policy formulation of maximum entropy reinforcement learning. So essentially, the off-policy formulation stipulate that we can optimize, we can still find the optimal policy by using samples that have been generated by another policy. And so this allows us to use what is known as experience replay mechanism, which essentially consists in storing the past experience of the agent in a sort of memory unit, and to use these samples in order to optimize our actor and our critic estimators. So experience replay, even though it have been a very central mechanism of deep reinforcement learning, has been quite a bit ignored so far by the community, even though some of the big name of the field have been pointing out that this mechanism have a real effect. It can either make your agent converge or not in some cases. And so we've been able to see that in the literature as well, which motivated ourselves to work on this topic as well. And essentially, recently, we find in this also recent survey, like we found the differences in the replay mechanism that takes place in biological system and the one in our digital system. So the difference between replay in brain essentially and the difference in our deep learning system. And so here I've listed some finding related to reinforcement learning essentially, but if you're interested, they also talk about supervised and unsupervised learning in this paper. And so what we found is that replay, in fact, is temporally structured. So when we learn a new task, we don't just remind ourselves of uncorrelated part. So if you want to learn a sport, you will rather use temporal sequences in order to replay and to improve your performances. The second point is that replay is modulated by reward. So some samples are have more information contained within themselves in order to learn a new task. So if you want to learn painting, there's no benefit of learning how to program. And the last point is that replay is treated differently for novel versions, novel versus non-novel input. So the fact is that our brain tends to give way more importance to new input rather to the old one. And so this is totally ignored by the experience replay mechanism actually. So we propose a new method which we call by bio-inspired replay, bio-inspired experience replay, where we essentially try to incorporate these limits into one framework. And so the idea is that we divided the experience of the agent in two memory units. The first one, we store all the temporal sequences of past experience, and we sample from it temporal sequences and not now uncorrelated samples. And on the second buffer, which is a smaller one, we store what we believe is the best interaction made with the environment. And so we select them based on the criteria, based on the Q value for some very particular reason. But the idea is that it was found that by focusing on the highest quality region of the environment, it is possible to learn faster and to learn a better policy. So this is essentially all the elements of the proposed learning base adaptive control structure, which I try to summarize in this diagram. So as you can see in the middle, we only have the Ph.D controller. So the model-based structure is our Ph.D controller. So we use adaptive pole placement in the poles domain, and we use our mapping to transform them back in the gains domain in order to derive the Ph.D control law. And the whole structure is optimized in an offline fashion using this soft actor critic algorithm, and the exact same structure is used online on the real robot. And so now I'm gonna present you how we use this architecture in an experimental setup. So in order to validate our method, so this is the result of these 3 years of thesis. So I'm just gonna focus on the last experiments we did, which was to use this cubic shape vehicle, this Blue Rove platform, in order to perform station keeping. And so the idea was to make the vehicle stabilize at different set point in space under varying current disturbances. And so because the vehicle is only equipped with an IMU unit, we had to use an external positioning system, which is composed of a camera, and we essentially put a QR code on the back of the vehicle in order to have an estimation of the positioning using also a Kalman filter. And this is just to give you an illustration of the disturbances we use. So we use quite strong thruster to generate water displacement in the tank. So we used a value of a disturbance that was too strong for human operator to stabilize the vehicle as desired. So essentially, we drive the vehicle by hand ourselves, and we augment the disturbances until we could not stabilize the vehicle by ourselves. And so this is just to show how beneficial this approach can be and how robust it can be against very strong current disturbances. So in order to train our reinforcement learning algorithm, we use a very basic, I would say, we've used a lot of reward function during this thesis, but we found we've experienced that the simpler, the better result we were having. So here the reward is essentially just a function of a distance to the set point. So if the error on each set point is 0, this is the only way to maximize the reward. So by doing that, we are sure that only the desired behavior is the one associated to the maximum value of the reward. So we kind of constrain the agent to learn what we really care about. So I will pass quite quickly on the hyperparameters. So one of the good benefits of the maximum entropy reinforcement learning is that this by maximizing entropy, the resulting performance is way more robust and doesn't need any fine-tuning, any exhaustive fine-tuning. So we essentially use exactly the same neural network architecture and hyperparameters that have been proposed in the original paper of the algorithm and that have been used over a tenth of different agents. So we use the exact same architecture. So there's no contribution there, but that's one good point, is that you don't need any hyperparameters fine-tuning in order to use this algorithm. So now, in order to make sure that what we learn in the simulator will remain valid in the real world, we had to use what is known as domain randomization. So in order to build the policies that will be valid on a different mode, we have to make sure the agent explore and experience a lot of variation of the process. So this is something we've been already able to have experience with earlier. So this was a work with ONERA, the French National Aerospace, where we essentially used the soft actor critic algorithm to teach a robot to perform target rallying. And so we split the training environment into sub environment of that different complexity. And so we then make the agent transit from one complexity to another based on its current performances. And what we found is that only the controller that was trained using this strategy, so who would explore different variation of the training environment, was then able to complete the task in the real world. And so we've been also working a lot in this thesis about this sim to real transfer problem. And essentially what we did for this experiment is that we train our model in an infinite variation of the training set, where we will vary the complexity of the environment in terms of disturbance complexity, disturbance forces, and also in terms of failure mode. So we will have sometimes some power loss and so on. So the idea is to make sure that we experience so much variation of the environment that then the real world will just seems like another variation. So that's the whole idea of domain randomization. And just for illustration, I've made a quick video of just showing you how it looks like. So we do our training using Gazebo, the Gazebo simulator. So here it's not the vehicle I was talking about. It's not the BlueRov 2, it's the RexRov platform. But it was just an example to show you the idea that here we want to teach the robots to follow a straight line while being subject to external disturbances and power loss. And so essentially at the beginning of the training, we will see that, so this is the view underwater. The vehicle will shake a lot at the beginning of training. It will drift a lot. We can see here it's drifting quite a bit. And after a few times, a few moments of training, which happen quite quickly, we will see afterward, the vehicle is starting to take better and better action and to compensate for the disturbances, even though we cannot measure them. So now this is just some training curves of obtained using this architecture. And on the top left, we can see the return of the agent. So in blue, you have the agent that have been trained using the classic experience replay, and in green, it is the agent that have been trained using our bio-inspired experience replay. And in yellow, it is a model-based optimal controller, which is fixed, so it's non-adaptive. And so what we found essentially is that by only modifying how we use the past experience of the agent, we were able to learn faster and in a more stable way. So we were able to reach the stability of a optimal model-based controller, essentially. So now to finish, I will just showing some of the results obtained from the experiment. So we did this task of station keeping 10 times for each controller. So without disturbances at first and with disturbances in the second time. And so essentially what I wanted to say here is that this is the result for the case where no disturbances were used, and a value of 0.2 actually is satisfying. So it can be considered that the task is completed. So without disturbances, both controller is essentially able to complete the task. But we can already see that the learning-based adaptive controller is doing way better than the purely model-based one. And what I wanted to highlight here is that why the model-based controller is failing more, even without disturbances, is because we had a very non-perfect model of the vehicle. So the vehicle we use is a modified version of the vehicle with lots of different parts added. So things such as the momentum, the added mass matrices, and so on, we didn't use exactly the perfect value of it. So that's why we believe the model-based controller is doing this bad compared to the learning-based one, even without disturbances. But this was quite good for us, because this means that even if we have a bad model of our vehicle, using our method, we can still design a control structure that is satisfying enough to complete the task. And secondly, now the result with disturbances, we can clearly see a difference between the two models. And so here again, the learning-based controller is doing way better than the purely model-based one, which was often drifting so far from the set point that it was not able to come back in the field of view anymore. So we had to drive it back in the working area by hand. So yes, to conclude, I will just finish this presentation with some of the current research we are going on now. So so we've been able to publish 7 peer-reviewed papers within these 3 years of PhD. We've been working a lot on a ROS package. So for the moment, the package is on a private GitHub, but we might open it later on with the future collaboration that is still going on with our industrial collaborator, Naval Group. And so on the ongoing part, we are working now on, so I proposed you a presentation about a linear model, a linear control structure. So the P.I.D. is considered as linear, even though with the adjustment mechanism, it makes it non-linear, but we want to use a non-linear adaptive control structure in the future, such as L2 adaptive control and over more non-linear control law. The second one is that we are working on using performing the reinforcement learning process online on the robot directly, because we've been able to see that we were able to exceed the performance of the model-based controller very rapidly, so within 30 minutes of real-life training. So we believe that we could perform this training in real life directly on the robot. So we don't need to train for hours before reaching satisfying performances. And at the end, one thing we are doing now is multitask / multi-agent. So essentially, I'm training my algorithm on one robot, and I'm using it on another one, or I'm trying to learn to perform target rallying, and I use it to perform, for example, trajectory following. So this is some stuff we are exploring now, and we have already good result for for the moment that we hope to publish soon. So this is very interesting and a very hot topic in the domain of reinforcement learning. So we don't want to have one model that is specific to one robot, but instead to have to learn to adapt, how to adapt. So we don't want to learn to adapt to one specific robot. We want to learn to know how to adapt to a given process variation. And to finish, I will just finish with some future research I would like to tackle in the near future. So first is offline reinforcement learning. As I said, this is an off-policy method, so we don't need to use the policy that we are optimizing. So this means that we can control the robot by a human expert, for example, and use this data to optimize a policy in the background, which is way more safer than optimizing it online. The second point is internal disturbances. So in my PhD, I was mainly focused only on external disturbances. And the next step of this whole research program is to tackle the internal disturbances. And it will be the case of a future PhD student who already started, sorry. And finally, I'm really interested also in reducing value overestimation, which is really the big problem in reinforcement learning and one of the big issue when we want to transfer such model in the real world. So that's one of the research topics I'm aiming to go further on in the next step of my research career. So thank you again for your attention, and please let me know if you have any question.
Thank you, Thomas. I'm sure the jury have a lot of questions, don't worry. So, okay, you're in time, that's good. So we are going to start questions.